Hey, welcome to the introduction to the new International Baccalaureate Standard Level Maths course. This is going to be firstly examined in 2014, and the idea of this presentation is to have a look at the prior knowledge the IB organisation expects you to have before you start this course. This presentation is based on work from the Pearson's new IB course 2012 edition textbook. And so I've taken some screen clippings from there, and I encourage you to get your own book there and have a look. For the moment, let's have a look at what the IB has listed as prior knowledge, and you can see this on their website. We'll just read through it together, and there are some major differences between what the IB expect and what many schools in Australia are teaching prior to the start of this course in about Year 11. I think we can give a tick to most of these things here: routine use of addition, subtraction, multiplication and division using integers. This line up here, simple positive exponents, not too bad. Simplification of expression involving roots, square roots or radical signs. Could be a question mark there for some people. Prime numbers and factors, common divisors, least common multiples, usually done by the end of Year 10. Simple application of ratio, percentage and proportion. Yes. Definition and treatment of absolute value. Now this is usually not taught before Year 11. Rounding, decimal approximation, significant figures including appreciation of errors. Yes. Usually have some understanding of that. Expression of numbers in standard form, yes, usually in about Year 10 with powers or exponents. Here we go, concept and notation of sets, elements, universal set. Now this is not usually taught before Year 11. Operation on sets, union and intersection, no. Commutative, associative and distributive properties, question mark probably. Venn diagrams may be in probability, so put a question mark there. Number systems, natural numbers, integers, yes, but what about the symbols? The IB like you to be aware of the proper mathematical symbols for these sets. Intervals on the real number line using set notation and using inequalities. Now the IB have their own notation which differs a little bit from some other books, so we have to have a look at that. Mappings of the elements of one set onto another, ordered pairs and so on. So probably we'd have to say there's a fair bit there in sets and numbers that we would need to have a look at, and that's what we're going to do in this presentation, bring you up to speed for the start of this course. And if we come down here to algebra, manipulation of simple algebraic expressions involving factorisation and expansion, give that a tick. Rearrangement, evaluation and combination of simple formulae, yes, usually. Linear function, its graph, gradient, y-intercept. Addition and subtraction of algebraic fractions. The properties of order, relations greater than or less than signs, yes, possibly a question mark for some people. Solution of equations, inequalities in one variable, usually okay. Solution of simultaneous equations in two variables, intersection of straight lines and that sort of thing. Year 10 would give that a tick. That's not too bad. What about trigonometry? Angle measurement in degrees, compass directions, yes, usually. Right-angled trigonometry, SOHCAHTOA, and that sort of thing, sine and cosine, simple applications, yes. Pythagoras, yes, that should be okay. Geometry, simple geometric transformations, translation, reflection, rotation, enlargement, congruence and similarity. Generally okay, maybe a bit of a question on some of the transformation work there. The circle, its centre and radius area, arc, sector, yes, usually a bit of a question mark on perhaps arc and sector. Perimeter and area of plane figures, properties of triangles and quadrilaterals, including parallelograms, rhombuses, yeah, probably not too bad. Volumes of prisms, pyramids, spheres, yes, probably around year 10 work. Okay, so let's come down a bit then, just to finish this off then. So coordinate geometry, concepts of dimension for point, line, plane in space, equation, probably okay. Parallel and perpendicular lines, yes. Geometry of simple plane figures, parallelograms and stuff, probably yes. Cartesian plane, XY coordinates, yes. Midpoint of a line segment and distance between 2 points, year 9 and 10, should be okay. Descriptive statistics, collection of raw data, it's a display of data in pictorial and diagrammatic forms, pie charts, pictograms, stem and leaf plots, bar graphs, yes, year 9 and 10. Obtaining simple statistics from discrete and continuous data, mean, median, mode, quartiles, yes. Calculate the probability of simple events. So that's not too bad. So if we go back up now and look at what we've done here, the subject of this presentation now, based on Pearson's new textbook, are the areas where it's been crossed here. Okay, so the cross up here, and here we have another one, and right through this section here particularly. So keeping in mind, of course, that the IB organisation does like you to use notation well, and so that's what we're going to start with. So let's have a look at our first little area here where we might need some work. It's to do with the real number line and sets of numbers. So the sets of numbers here can be seen on this diagram here from Pearson's textbook. You've got a scale here which consists of whole numbers. So this is a set of integers, positive integers on this side, negative on the others. So we actually have Z is the symbol for this, coming, I think, from the German Zahl for number. So these are the positive integers here, and over on this side, these -1, -2, etc., are the negative integers. So that's what we usually put our number line scale in, is an integer one, and then we try to position other numbers on that scale. Let's have a look at the next possible set that we might be interested in, and the next possible set really, I suppose, is the rational numbers, these here that are ratios of integers. That one, a third, and, well, this can be written as a ratio of integers. Do you remember it would be neg 2.58 over 100. So these I've got circled here are called rational numbers. Okay, so these are rational, that's equivalent to rational numbers, and rational numbers are ratios of integers. So therefore you have any of the numbers that have one integer over another, or are a terminating decimal like 2.58, that can be written as a ratio of integers. So that's our rational numbers. And what are the irrational numbers? Well, have you come across these before? They're the numbers that can't be written, here they are here, as a terminating decimal or a non-repeating decimal. Oh, I've left out a rational one here. Here is neg 999 over 1,000. So that's rational as well. These others, you know, you might remember pi, 3.142, and it keeps going. And it's not recurring. Some numbers that are decimals, like if you took, for example, 0.3 recurring, that's 0.3333. You might say, well, that doesn't stop, that can't be rational. But if you think of, let's call it x is 0.3333, etc., then if we said 10x was equal to 3.333 recurring, and if we took the x away from the 10x, so let's do that now, we would have 9x equals, what have we got, 3 up here, 0.33, take 0.33, we've got 9x equals 3, or x is 3 over 9, or a third. So recurring decimals through this sort of treatment can be shown to be rational if the decimal recurs. However, if it keeps changing, as with pi, or with the cube root of 10, or the square root of 2, or minus the root of 3, then they are said to be irrational numbers. You can't write them as a ratio of whole numbers or integers. Okay, so there's no actual special symbol for the set of irrational numbers. Let's try and summarise all our numbers then in a diagram. Okay, so here's our diagram, a little table underneath. So you can see the sets get bigger and bigger. Haven't actually mentioned this one here, the set of natural numbers, or the numbers that you might say occur naturally. If you don't have anything, you would represent that by 0. If you've got one object, it's 1, 2 and 3. So that sort of explains the set n of natural numbers. And what's the next set up from that? Well, if you want to indicate direction, so you get positive and negative wholes, including 0, it's a set of z. If it's the positives, it's z plus, the negatives, it's z minus. And so the positive integers start at 1, 2 and 3. The negative integers are neg 1, neg 2. You might include, all integers would include 0 in the middle there as well, as we'll come down and look at this table in a minute. So then a bigger set then are the set of rational numbers. Can you just keep in mind that integers, or all the integers, are also in Q, in the rationals? Because take an integer, take 2. Is it a rational number? Yes, it can be written as 2 over 1. So any integer is in the rational number set. So can you see from the diagram the sets are getting bigger and bigger? The whole real number set contains all of them. The rational numbers contain the integers and the natural numbers n, and then you've got the irrational numbers here. So the whole big set is called the set of real numbers. Now this notation is very, very important in the IB. The organisation likes to see mathematics represented well with its own language. So it's very, very important to know these symbols. So here's the summary down here now in the table from Pearson's, and that is a set of positive integers up here, z plus, natural numbers here, n, including 0, and the whole set of integers there. Rational numbers, any number that can be written in the form P over Q, a ratio of integers. So rational is an easy word to understand. It's ratio now, and you've got those sort of clues there as a hint to what they're going to be. So we've got whole sets of numbers, and we need to look at that, because this was one of the pieces of prior knowledge that we felt we didn't know from year up to year 10 work. So let's have a look now at some of these ideas of sets of numbers. So the first thing I'd like to do is to say, well, let's look at a set C, and we'll call set C 2, 4, 6. Now I'm introducing a squiggly thing here. You can see it's been used up here, that squiggly bracket, to mean set of. So it's a set of. So C is the set of those numbers. Let's take D as being a set of just 2, 4. Now, you can see that D is contained within C. if we were to draw a diagram, C is 2, 4 and 6, and D is only that much. So D is contained within C, and we put that in. I think the easiest way to remember it is D is contained within C. It's like the less than symbol, isn't it? In numbers, 2 is less than 3. So it's sort of the same idea. So D is contained within C. D is less than C. If you said, let's come down here a little bit further, if you let D be the set 2, 4, 6 also, then you could say that D was contained within or equal to C, because they're the same set. Also, C is contained in or equal to D. So you could do either of those two if they contain the same elements. Now this up here is very, very important. D is contained within C like that. Means D is what's called a proper subset of C, because it doesn't contain everything that C contains. It's smaller in the number of elements. Some of the elements in C are not in D, so that's called a proper subset. Okay, so that gives you some idea. You might like to think now, and this is an exercise coming up later, what about the sets of natural numbers and the real numbers? Well, the natural numbers are contained within the real numbers, so we could write that from before. So we're getting into a bit of notation here. It's important to probably note this down and try and remember these notations. We've got another symbol, of course. We can write 6 is a member of Z or Z plus. So this means a member of or an element of. So here that little E sort of looking thing means is an element of. So we can use that as well. And if we wanted to represent some sets, there's a few ways of doing it. We could look at the set A and we could list out its members. I don't know, neg 2, neg 1, 0, 1, 2. You can see this is fairly clumsy if the set gets very, very big. So there are shorthand ways of doing that. The first one to say A is the set of here X, and we read this as such that, or we're going to follow up this with a rule now, X such that, and then we're going to put, well, we could list them out again, neg 2, neg 1, 0, 1, 2, or we could make it even more condensed here, the set of X such that. Now, rather than list them all out, we could say X is a member of Z and neg 2 is less than or equal to X is less than or equal to 2. So that inequality statement there is important. That's an important abbreviation, saying that X is a member of Z and it's between neg 2 and 2. So we need to build up our set notation. It's called set builder notation, to make it a neater mathematical expression. As I said, the IB likes to have a neat mathematical language to go with the subject. What about saying, well, what if we have a set A this time, which is, or I don't know, all the integers, all positive integers larger than 5. Now that goes on, that's a big set, isn't it? It keeps going. So we could say that is the set of N, which is a member of, I don't know, Z, integers such that n is greater than 5. So that would be a way of representing those integers, all the positive integers larger than 5, without having to write them out. Well, you can't write them out, can you? They keep going for a whole infinite real number set. Okay, so are you getting the hang of it? This notation is important. So let's come down here a little bit, and I've got some ideas of sets overlapping. So I don't know, here's what's called a pictorial representation of sets rather than our algebraic notation, and this is called a Venn diagram, or there's two of them here. Venn diagrams are a pictorial or graphical representation of sets of numbers. So what do these pictures mean? I think you can probably see the idea here, and that is that set A is this first circle in here, and set B is the second. And what do you notice? They overlap, or we call the word intersection. So this is the symbol A intersection B. So what would be an example? Well, let's say A was the set from, let's say, neg4, neg3, neg2, neg1, 0, 1, 2, and B was the set, what can we say, 0, 1, 2, 3, 4, 5 and 6, something like that. And you can see that though these two sets do have elements in common, or they do intersect. So here, oops, just include the naught there. So we would have an intersection here. I don't like that. I just want to just rub this out here, I think, and put it more clearly. 0, 1, 2 are in both sets. So what's in here? The intersection of A and B would be the set of values 0, 1, 2. So we could indicate that there. We're looking at the intersection of sets, that little n-type symbol there, as being where they overlap. What elements are common to both? Okay, what about over here? I think we can see the word union and look at the symbol. A union B means we're going to unite the whole lot. We're going to unite the sets and have everything that's in both of them. So if we use the same sets as what we have here, then what would the union look like? It'd be neg4, neg3, neg2, neg1, 0, 1, 2, and we have to include everything in B as well. So we have that set there, which includes the intersection and all the elements in both sets. So that's uniting the sets. So does that make sense? Then I think starting to get familiar with the notation and ways of thinking about sets and their overlap and what's in one and what's in another. So let's come down now and look at where we might have perhaps sets of numbers that are represented on a number line, and what we're saying here is we're looking at an interval. Here's another word, an interval on the number line, and we want to represent the numbers there in a way. So if we looked at these, then what could we do? So here we could have an inequality notation like this. Can you see that it has to be equals here and here because that's shaded in? It includes both ends. So we could write it like that, or we could use a set notation for that interval. X is a member of the set going from 2 to 5. Now this is called a closed interval because it's closed on both ends, and this means it includes the ends. So that is equivalent to saying you can have the equals. Let's have a look at a variation of that and say here, well, we won't include there, so we're not included. Unshaded means not including the ends. Might have had that in year 10, not including the ends. And so here what we've got is the interval from -3. Oops, I've just included it, so just get rid of that. -3 to 1. And so this is called an open interval, doesn't include the ends, so it's a member of. Now we do the backwards sign here. -3, 1 backwards, which means it is not included. So this is these ends here, different symbol, not included. So that's important there. And so this is called an open interval. So we're getting some words here surrounding this word interval. And so you can see that the notation is quite interesting and neat. It's good language mathematically, very precise. So let's have a look at this one down here. Can you do it? -4 is less than or equal to x is less than 2, because this is shaded, so -4 is included. This is not a shaded circle, so the 2 is not included. So this is half open, this interval, because it's closed on one end. Let's have a look. X is a member of the set -4 and 2. Now 2, we use a backward sign there to show that not including. It does not include that end there. And so this is called a half open interval. So only one end is closed and has equality there, which means it stops right on that number. So these are all called bounded. So we'll just come down here a bit. These are all bounded because they've got a bound on each end. They might be closed, they might be open, or they might be half open, but they are bounded because it stops at both ends. So it has endpoints, if you like, that you can't go past. But what about something like represented down here now, where you can see it's starting at 2, so it's x is greater than 2, no equal sign, because that unshaded circle means it's not included. But then it keeps going. When does it stop? Well, it doesn't. So x is greater than 2, it keeps going. This is called a ray. It's not actually an interval, closed interval, on the number line. And so we could write this as x is a member of. Now, how are we going to do this? Well, we're going to say, well, on the end here, it's actually open. We're going to put here, this way, to infinity. We can do it like that for that particular type. And showing that it's not including the 2, and of course you can't include infinity. There's no end point to that one there. So that's our notation in that case. So this is really what we would say is our first example of an unbounded set or interval. It hasn't got bounds on both ends. So we're going to stop in a minute. I'm going to give you a chance to practice some of these ideas. So come down here and let's summarise what we've just been trying to do. There's actually 9 different combos here, and it's important that you do study this and remember it. So I like the way Pearson have presented this graphical approach here. So over here, X is a member of the set A and B, which is closed. So, and these two are therefore included. It's bounded because it's got two ends, so you would sketch it with that graph there. Just getting used to the idea that this pair means the ends are included. So they're working nicely there by putting it on the diagram. What about this one here? X is a member of the open set between A and B, because what have they used here? In this one, they've used these symbols over here, back at the beginning. So it means the two ends are not included, so it's open. It has got ends though, so it's bounded. Okay, what about the combo? Here, on this one, it includes this end, but not the other. So it's, if you like, half open, because this end is not included, the end of the domain there, and therefore it's half open, and we would, if you put it on a graph there, we don't include B, so you could put a circle type thing there also, as we were doing before. And then the next combination, I think you're getting the idea that the closed one is included, so we'd make a shaded circle there and a unshaded circle there. It's half open because there's no equality to the bound on the bottom side, but they're all bounded. So what about this one here, next one? It's half open because this end is closed off. You can equal A, but there's no upper end, so it is unbounded. Okay, so what about the idea here? Infinity on one end, of course, means it's completely open up there, unbounded, and in this case this one is unbound on this end as well. Sorry, it's bounded on this end, but it's open because the A is not included. So see there, the A is not included. That makes it half open, but it's fully open actually, because it's open and unbound on the other end. So here, half open in this one here, again, because we've got equality to B, so that means it's shaded circle there, it's closed on that end, it's not closed on the other end, so it's half open. It's also unbounded because it can keep going there in the negative direction. It's a ray, so there's lots of ways of referring to this. An interval, closed on each end, or bounded on each end, and then a ray being open, and so on. So coming down to the last one here, it going off down there, so it's unbounded. It's also open because here B is not included. You could put an unshaded circle in there. So work through those carefully. The real number line, of course, is unbounded. So here, how would you represent that? We've got the idea of no bounds on the end, open, so it's just continuous. All right, do you think you're ready? Maybe you'd like to pause the presentation and look through those and just study them again and see what you think. But if you want to have a go, come down here. I've taken the Pearson's exercises here and just put them there for you, so it goes down to there. So as you want to move on, pause the presentation. You can pause the presentation now, do the first half a dozen problems, because they're all the same, working on the number line, and then check your answers and so on. So I'll go down to the answers so that you can access them in a minute. I've put them out of sight here, so they're the first 6, so that when you've done those, you can pause the presentation, or not pause it, fast forward it, come down, freeze this and mark your work. Okay, so that idea, and then we go on, of course, to the rest of these. as you go. So the other answers then for the rest of them, so if you need to access these in a minute, or later on rather, you can fast forward and come down to that. Freeze it, mark your work, and away you go. All right, so I'll leave you to do that, or go back up here to the starting set, and then you can move it around according to what you like. All right, so I encourage you to pause the presentation now and practice, and then what I'm going to do is to move on to the last little note there, which I think was on modulus. So can we come down and have a look at that? Okay, so I'm going to take Pearson's definition of this, quite neatly explained here. The absolute value or modulus of a number is, if you like, its size or its distance from the origin on the real number line. So distance is positive or 0, so that's a secret thing here. It's talking about the size of the number, if you like. How big is the number -3? How far from the original 0 is it? So the size of 3 is just 3 units, isn't it? So modulus or absolute value doesn't have a sign in front. Okay, so if we want, here's its symbol, the size or modulus or absolute value of 3 is just 3. The size of positive 3, how far away from the origin is that? That's also 3. So consequently we have this definition here. The size of a number A is just equal to itself. If it's positive, that's what it's saying here, positive or 0. It equals the negative of the number if the number is itself negative, because that's what we're saying here. How do you get from -3, taking the modulus of it, to 3? Well, you can multiply by -1, and that would give you the 3. That's what the definition is saying here. Modulus can't have a sign, it's a distance. It's a absolute value only, just a size value. So here are the 4 properties of modulus. The modulus in any number is greater than or equal to 0, it can't be a negative, that means it's a positive number. The modulus, and we've just done that, the modulus or absolute value of a negative number is the same as a positive, because they're the same distance from the origin, from O, and if you have the size of a product, it's equal to the product of the 2 sizes, because they're all positive numbers, and similarly here. If you're looking at the size of a quotient, A divided by B, then it's the size of A over the size of B. Alright, so that's pretty much okay. Let's just maybe draw a picture of a couple of numbers here. So let's take the number 4 out here, and we say, what is the size of 4? Well, the size of 4 is that distance, it's just 4. If we came over here, however, and said, what is the size or absolute value of -2? It's this distance here, it's 2. Its negativeness disappears because just looking at the size or the distance from the origin. Okay, so let's come down here and look at the next little statement about using absolute value or modulus. If A and B are real numbers, we're reading this now, the distance between the 2 points with coordinates A and B on the real number line is B take A, or the absolute value rather of B take A, which is equivalent to A take B. Why have we got that? Well, we might not know how big A and B are. So if we say, well, what's the distance between the points on the number line -2 and 4? What is the distance between those two? Well, you could say, oh, distance this one minus this one. It's -6. Uh-oh, no, distance has to be positive. So we put a modulus or absolute value sign around that and just say it's 6. So the modulus or absolute value sign means we don't have to know which one is positive or negative. Now, if we did it the other way, 4 take -2, that's 4 plus 2 is 6. We didn't need the modular sign there. But for safety, it's always good to put that to ensure that the answer is positive. It is supposed to be a distance, not involving a negative. So if I say to you, P is one number and Q is another number, they are on the number line, and I want you to find their distance, but the distance between them rather. So the distance is the modulus of P take Q, and which will be equal to the modulus of Q take P. Because if you didn't know which one was bigger, P or Q, when you took them away, if you removed their sign, when found the absolute value of it, then you would always have a positive. So you don't know whether P and Q were in this order, and you would have gotten a negative or not. So for safety's sake there, if you're trying to find the distance between 2 points on a number line, you can say, I'll just find the absolute value of their difference, not knowing whether that difference will be positive or negative. All right, so let's have a look at a little table from Pearson's there of this summary. So if we say here the size of our number x is less than or equal to a, how big could a be? Well, I like to look at the graph first and then we'll come back to this. So let's make number 1, let's try to represent the modulus of a with absolute value of x, is less than or equal to a. Where could x be? Well, it can't be more than a either way. But it can be either way because its size is less than a. So therefore we would then come to point 2 and say therefore x lies between neg a and a. Are you getting the hang of it there? Here we have the absolute value of x is strictly less than a. So you can see here the unshaded circles means you can't include those endpoints. Okay, so it's a bounded but open interval. So what that means is we're going to say x can be from neg a to a. What about the size of x is greater than or equal to a? Well, it means it's got to be outside this, outside here. So we've got a split inequality statement. Can't make a single statement because x can't obey this side and this one. And that's a salient point, important point. When we write this and jam x between the two values, it means that x is behaving according to this and this at the same time. So you can put it as a single inequality. Down here we can't write this one like that because x can't be obeying this part of the inequality and that part at the same time. So it has to be a split interval. We must write it in that split form. And then the same thing here, the size of x is greater than a means it's outside here. But it's not including a because there's no equal sign in our inequality back at the beginning. So again, it's a split interval. X can't be obeying that rule and that rule simultaneously, so we write it as x is less than neg a or x is greater than a. Well, we're coming to the end of that prior knowledge, trying to fill in the gaps that might exist. So let's have a look at some exercises now on this stuff then. So here we have it. These are the questions from section 1, chapter 1 of Pearson's textbook, where we are looking at trying to write these using notation. So you can check back at what we've just done here, have a look at those, and then have a go at these here. So I'll just take you down to the answers here. There are some answers for you. So don't look at those for the moment, but I'm putting it there so you can forward the presentation as you do a few. So as you do a few here, you freeze it, then go back and pick those solutions up and mark them. I'd suggest you do maybe 33 to 36 as a batch, go and check it, and then the next batch and so on. Make sure you're getting them right. Okay, well, I hope you enjoy that. I think it's a very, very important starting point for the International Baccalaureate maths subjects, that you do pay attention to the language of the subject. The IB do consider it very important, the notation and so on. So I hope this helps you get started. It's an exciting course. There's explorations in it for you later on as part of the internal assessment, and I think you'll enjoy working with it. So there will be other presentations in this series, but I might see you then. But for now, it's cheers from me.